In Chapter 11, we're going to be looking at sequences and series. And sequences, you've seen before. If I gave you an ordered list of numbers, something like this. If I gave you 2, 4, 6, 8, dot, 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 dot. There's a sequence. I could give you a sequence like this. I could give you 1, 1, 2, 3, 5, 8. Do you see the pattern? This is actually a famous sequence. It's called the Fibonacci sequence. And I start with my first term. There's my second term. And notice I find this third term by adding these two. I find this term by adding these two. I find this term by adding these two, and so on. So that's actually called the Fibonacci sequence. So a sequence is an ordered list of numbers. And each of these entries is considered a term of my sequence. Typically, we'll call this very first value the first term, or first position, second position, third position, and so on. That's typically what happens. Now, we have some different types of rules that we can write, and one is called a recursive rule, and one is an explicit rule. And they each are good depending on what type of a sequence you have and what you want to do with it. A recursive formula defines the terms by relating each term to the ones that come before it. Here's just an example. If I tell you my first term, a sub 1, is 4, I can give you a rule that helps you find all the terms after that. Like you would know from this that the first term in my sequence is 4, so the very first number would be 4. We'll call him a sub 1. The second term would be in the second position, and we have the next number. Now, how do you find a sub 2? We find a sub 2 by using this rule. We find a sub 2 by finding a sub 1, who is 2 minus 1 is a sub 1, and adding on 2. So we need to take the first term, add on 2, and that gives us 6. If we want to find the third term, I'm going to use this rule again. The third term, plug 3 in here, 3 in here, tells me I find the a sub second term. I'd find the a sub third term by taking the a sub second term and adding on 2. Well, the previous term is 6, add on 2, and I'm up to 8. So again, I can find all of these terms. The problem is with the recursive rule, well, let me find one more. Let's find the a sub fourth term. The a sub fourth term, I plug 4 right here and right here. And so my a sub fourth term will be take the a sub third term and again add on 2 each time, which means I need to take the number who is in front, add on 2, and I'm going to get 10. So it would be pretty easy to write this term, the sequence terms. We get the pattern that you started with 4 because a sub 1 was given to us as 4. Right here we have a sub 1 is given to us as 4, and we just keep adding on 2 each time. So if we're going to write down the terms of a sequence, it's very nice to know the recursive rule because I can write down the terms quite rapidly by just seeing what the process is, that I have to take the term in front of him and add on 2. Now, what happens if I want to find the a sub 50th term? I'm not particularly fond of this recursive rule if I have to find the 50th term because that means I need to know the term right in front of him in order to find the 50th term. In order to find the 50th term, I have to know the 49th and the 48th and 47th and so on. I'd have to find all the terms of that sequence. So we like to have rules that are explicit rules as well. Explicit rules define the rule in terms of the nth position. For instance, if I give you this rule, a sub n is equal to 2n squared, if I asked you to find the 50th term for this sequence, it's very easy to find the 50th term, a sub 50. All I'd have to do is plug 50 into the rule. I'd get 2500 times 2, My answer would be 5,000. So the 50th term, or any term, any position's term, is very easy to find if we have an explicit rule. All we have to do is plug in n, and boom, we'll have the answer. So if you want to write down the terms in a row, if I want to write the first term, second term, third term, fourth term, and so on, I actually prefer to have the recursive rule because I know what process I do. I use the term in front to find the next term. As opposed to my explicit rule, I can find any term by just plugging n into my rule. Okay. Now we have a situation that we'll look at two particular types of patterns with a lot of detail in this chapter. And the first one is actually shown here. We'll end up calling this process a geometric process. But suppose you drop a ball from a height of 100 centimeters, and it bounces back to 80% of its previous height. How high will it be after its fifth bounce? Okay, so we know we're starting here, and it's going to go down 100 centimeters, and then it's going to bounce. It's only going to bounce up to 80% of what it was. And then it's going to come down, and this will be its second bounce. And then it's only going to come back to 80% of the way it was. And then it's going to have its third bounce. And I want to know how high will it be after its fifth bounce. So here's after its first bounce, its second bounce, etc. And if we look at the terms, here's how far it comes down. After its first bounce, it's going to rebound up 100 times 0.8, or 80% of the value of which it had first come down. And then it's going to come down, and here's after its second bounce, it's going to go back up 80% of this previous value. And so this is after its second bounce, and I can see what ended up happening. After one bounce, I multiplied by 0.8 once. After two bounces, I multiplied by 0.8 twice. And so if I wanted to find out, here is after one bounce, two bounce, three bounces, four bounces, my 100 would get multiplied by 0.8, 1, 2, 3, 4, 5 times. And so I would end up, it would have come back up to this height. So 1, 2, 3, 4, 5 times it would have gotten multiplied by that 80%. And so it will have this last increase here would be about 32.8 centimeters is how far it's going to end up going up. And again, we're going to end up calling that idea geometric, where we keep multiplying by some type of a constant. Now we want to write an explicit formula to describe the height after its nth bounce. And an explicit rule, instead of going through and saying, well, if you take this one and multiply by 0.8, and take this one and multiply by 0.8, we want a rule that all we have to do is, I want the nth bounce. I want to go to the fifth bounce. I want to plug 5 in and boom, get my answer. And I can see that this rule is going to work. If I take 100 and I multiply it by 0.8 to however many bounces you want to have, that's going to explicitly tell me what I'll have for my answer. So an explicit rule, you plug in the n, the position you want, into your rule, and it will give you your answer. You don't have to go back and find the one in previous to it. Now in this next question, we have a sequence, and let's look at the pattern. So I can say I start with 2. My next number in my sequence is 6, 18, 54, 162. Do you see what's happening? It looks like we keep multiplying by 3 each time. And that does work. I multiply by 3. 6 times 3 gives me 18. 18 times 3 gives me 54, etc. And so on some of the questions, you may be asked just to write down in words what happens. And now we want to write the recursive formula for this. And anytime we have a recursive rule, we always have to tell where we start. We have no way of knowing what type of number needs to be in the first position unless we tell our person what we need to start at. And so we tell them a sub 1 is equal to 2. Some sequences you need to know more than the first term. But for this type of a pattern, as long as we tell someone where to start, We need some way of telling them, now just keep multiplying by 3. And our way of writing that out is like so. We tell them you can find the nth term by taking the one who's right in front of him, and the term who's right in front of a sub n is a sub n minus 1. Make sure this whole thing, n minus 1, is in the subscript. And then we need to take the term in front and multiply it by 3. So it's like, here's our first term, here's our second term, here's our third term in a sequence, and we're starting with the first term, and then we're finding the next term by taking 3 times that number. And we're finding the next term by taking 3 times that number. Or, I'll write it this way. We find a sub 3 by taking a sub 2 and multiplying it by 3. We find a sub 4 by taking a sub 3 and multiplying it by 3. We'll find a sub 5 by taking a sub 4 and multiplying it by 3, and so on. So that's recursively telling me I'm using the term in front of it to find the rule. Now, if I want to find the 6th and 7th term of the sequence, this is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. So to get a sub 6, all I have to do is multiply by 3. To find a sub 7, take the a sub 6th term and multiply by 3. So let's turn the page. Now we want to look for an explicit rule, and I'll put my paper down here in a second. I just want to flip that sheet over. And we want to find an explicit rule for the pattern. So we know we start with a sub 1, and we know that a sub 1 is 2, and this guy's a sub 2. And how do we get a sub 2? Well, to get a sub 2, we actually start out with 2, and then we multiply by 3. How do we find a sub 3? Well, we'll start with 2, and then we multiply by 3 and multiply by 3 again. How do we get to a sub 4? Well, we start with 2, and we multiply by 3, we multiply by 3, we multiply by 3. How do we get to a sub 4, the next term? We keep multiplying by multiplying the first position. For instance, the 10th term. If I had, here's the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th term. Here's the a sub 10th term. If we want to find that, we need to tell you what number we started with, the 2. And we see we keep multiplying by 3 over and over. And we actually will multiply by 3 9 times. So the number of spaces between the first term and the 10th term is 9 spaces. And so we're going to end up multiplying by that 3 9 times. If we want to go to the 50th term, we would start with 2, and we would keep multiplying by 3, and we actually would multiply by 3 49 times because there would be 49 spaces between those, the first and the 50th term. So here's our general rule for the explicit rule for this sequence. We start with 2, and we do repetitive multiplication by 3, and the number of times we would do that would be n minus 1 times. And again, you'll have quite a bit of practice with working with writing explicit rules for this type. Anytime you keep multiplying by the same value repetitively, it's called a geometric sequence. Okay, and then the last thing we're going to look at is this little chart. This little chart has some different area ideas and perimeter ideas for a particular square. And it says a spreadsheet shows the perimeters of squares that have sides from 2 to 12 units long. And so we can see that a length of a side for our first is 2. So I guess we would be starting with our first figure for a sub 1 is having like a 2 by 2 square. And so its perimeter would be 8, 2, 4, 6, 8. And then our next one, our a sub second square, and I'm not going to make it as big as it should be, but it has a length of side 4. And so if we found a perimeter, we'd have 4 multiplied by 4, we'd have 16, and etc. So we have a little spreadsheet that's showing us what the perimeter would be. And these make sense because if a length of a side for a square is each of these values, then the perimeter would be 4 times that for each of these. And so now it asks us, find the first 6 terms of the sequence showing the areas of the squares. Well, if we're going to have the areas of the squares, we know that area of a square is the length times the width. So we can see that the first area should be 4. The second area should be 16. The next area should be a 6 by 6 square, so it should be 36, etc. And here are my areas. And I kind of wrote underneath some of these little values that a length of a side squared, length of a side squared, etc. And I can see what my pattern is. It says, then find a sub 20. And if I wanted to find a sub 20, recognize if I keep going out here and get to that a sub 20th, I can see what the pattern is, that the first a sub 1 has a length of side 2. The second one has a length of side 4. And notice that I keep multiplying by 2. So a sub 20 is going to have a length of side of 40, which means its area would end up being 40 times 40, or 1,600. Now I want to write an explicit formula for that sequence. So an explicit formula, once again, is going to be I can just plug in 20 into my rule, and boom, it's going to give me my answer. So if we kind of break that down, we can see that the nth term, or go back even up here to the second term is going to have a length of a side which is twice as long as this position number down here. That's why inside here we have 2n. And then we want to find the area, so we know for the nth figure, it's going to have a length of side that is 2n. And then we want to find the area, so we would want to multiply it by itself or square it. So there's my explicit rule for that. The recursive rule would be a little bit harder to write, and we're not going to do that on this. And there will be certain values that we'll be able to find the explicit and recursive rule for particular patterns that are going to follow what we're going to call an arithmetic and a geometric. But there are going to be a lot that we're not going to be able to do yet. So now you're ready to practice.